Hello, students. This is Recitation 3. Task 1. At 4 community health centers on Cape Cod, Massachusetts, 15,164 patients were asked to respond to questions designed to detect depression. The survey produced the following results. So here on the left-hand side, we have the diagnoses. So we have mild, moderate, moderately severe, severe, and no depression. And then here are the number of people that received the following diagnoses. And so our learning objectives are to apply the fundamental probability concepts, so empirical probability, classical probability, and also to apply rules of probability, specifically part 1. So task 1, what is the probability that a randomly selected patient has experienced mild depression? So here, if we go back to the table, there's 3,257 patients that were diagnosed with mild depression out of a total of 15,164 patients. So if we take 3,257 and divide it by the total, we get 0.215. So that's the probability that a randomly selected patient has experienced mild depression. Now, what about the probability that a randomly selected patient has not experienced depression? So here, if we go back to the table, in the no depression diagnoses row, there's 8,613 patients that have not experienced depression out of the 15,164. So we can take this number and then divide it by this number. So we get 0.568. What is the probability that a randomly selected patient has experienced moderately severe to severe depression? So here, if we go back to the table, we have moderately severe and severe. So we'll want to add these numbers, and that will be the numerator, and then divide it by the total number of patients. So if we do that, we get the probability to be 0.115. Given that the national figure for moderately severe to severe depression is approximately 6.7%, does it appear that there is a higher rate of depression in the summer resort community? So in part C, we just calculated what the probability that a randomly selected patient has experienced moderately severe to severe depression, and that was 0.115. And so this is equivalent to, if you multiply this probability by 100, you'll get the percent of 11.5%. And here, we were told that the national figure for moderately severe to severe depression is 6.7%. And so when we used this resort community in Cape Cod, we got 11.5%, and that's greater than that national figure. And so the question is asking if it appears that there's a higher rate of depression in the summer resort community. That answer would be yes, because 11.5% is greater than that national figure of 6.7%. So feel free to pause this if you need to look at the solutions, but we already kind of went through the solutions. Okay, task 2. The following frequency distribution shows the ages of India's 40 richest individuals. One of these individuals is selected at random. So on this left-hand side, we have the different ages. And so the ages range from anywhere X in between 30 to 40, then in between 40 and 50, 50 and 60, 60 and 70, and then 70 and 80. And then here's the frequency. So here are the number of these 40 individuals that fall within these age categories. So what is the probability that the individual is at least 50 years of age, but less than 60 years of age? So at least 50 years of age, X is going to be greater than or equal to 50, but less than 60 years of age, we can write this inequality here. And so if we go back to the table to find where X is in between 50 and 60, where 50 is included, that would be this row here. And so there were 15 individuals in this age category out of 40 total. So 15 divided by 40 gives us the probability that we're looking for, which is 0.375. What is the probability that the individual is younger than 50 years of age? So that would mean that we could write X is less than 50. And so looking at the table, there's two categories that would fall within X being less than 50. So that's this first category. So if someone's age lies between 30 and 40, that's less than 50. And then same for here, we have less than 50. So we want to look at how many individuals are falling within these two age categories. So this first category between 30 and 40 years old, that's 3 individuals. And then between 40 and 50 years old, that's 8. So we can do 3 plus 8 as the numerator, and then we had a total of 40 individuals. So that would be 11 over 40, which is 0.275. So that's the probability that the individual is younger than 50 years of age. What is the probability that the individual is at least 60 years of age? So that means that it would be greater than or equal to 60. So we can look at this table, and so there's these two rows that correspond to an individual being at least 60, or in other words, 60 years or older. And so we can look at the total number of individuals within these categories. So that would be 9 plus 5, and then divided by the total number of richest individuals. So we would do 9 plus 5 divided by 40, which is equivalent to 0.35. Task 3. So the probability of A equals 0.55, the probability of B equals 0.3, and the probability of A intersect B equals 0.10. Calculate the probability, the conditional probability of A given B. So the probability of A given this vertical line means given B equals the probability of A intersect B divided by the probability of B. And so we were given that this value, probability of A intersect B, that's 0.1, and the probability of B is 0.3. And so when you simplify, you get 0.33 repeating. And this should be an equation that you had learned in class. Calculate the probability of A union B. So another equation that you were taught in class is that the probability of A union B equals the probability of A plus the probability of B minus the probability of the intersection A intersect B. And if we didn't have this minus the intersection, then we would be double counting the intersection because the probability of A, I don't really have a cursor that can draw right now, but if we had the probability of A, you can imagine event A, and then let's say probability of B, event B is overlapping A. So if you add those two, the part where they intersect is going to be counted twice when you add these two together. So we subtract the intersection one time, so that way we're not double counting that intersection. Okay, so now we can just plug in our values. And so here we have the probability of A equals 0.55, that's given. Probability of B equals 0.3, which is given. And then the probability of A intersect B is given as 0.10. So when you do the simplification, you get 0.75. Okay, what about the probability that of A union B complement? So by De Morgan's law, the probability of A union B complement equals the probability of A complement intersect B complement. And so this is equivalent to the probability of A complement plus the probability of B complement minus the probability of A complement union B complement. So essentially, if you look at this previous problem just for the equation, I know now we're dealing with complements to our set or to our events. But if we're just looking at this equation, you could add the probability of A intersect B, and so that it goes on this left-hand side, and then you could subtract the probability of A union B. So that's where I got this equation from, but now we're dealing with complements, so we get this. And so now the probability of A complement is 1 minus the probability of A. So that would be 1 minus 0.55. And then probability of B complement is 1 minus the probability of B. So that's 1 minus 0.3. And then the probability of A complement union B complement is the same thing as the probability of A intersect B complement. And this is also using De Morgan's law. And so the probability of A intersect B complement, that's the same thing as 1 minus the probability of A intersect B. And so that simplifies to 1 minus the probability of A intersect B we were given, which is 0.1. So you can do 0.45 plus 0.7 minus 1 minus 0.1, and you get 0.25. And those are just the solutions without the work. Task 4, consider the following probabilities. So here we have probability A being 0.4, now probability B is 0.5, and the probability of A complement intersect B complement is 0.24. Find the probability of A complement given B complement. So since we're given this B complement, that goes in the denominator, and then the numerator is the intersection of these two events. So that's the probability of A complement intersect B complement. And so we are given this numerator value as 0.24, and then probability of B complement is the same thing as 1 minus the probability of B, which is 1 minus 0.5. We were given the probability of B is 0.5, so I'm just plugging that in here. And so when you simplify, you get 0.48. What about the probability of A complement union B complement? So I'm going to use De Morgan's law, and so this equals the probability of A intersect B complement, which equals 1 minus the probability of A intersect B. And so this can be written as 1 minus the probability of, now I'm going to break down A intersect B. So we have probability of A plus the probability of B minus the probability of A union B. And so the probability of A union B equals 1 minus the probability of A complement intersect B complement. And so we get 1 minus, this was given, so 0.4, 0.5 was given for the probability of B, and then minus 1, and then I'm distributing this minus, so then it becomes a plus, and then this probability of A complement intersect B complement was given to us, which is 0.24. So when you simplify, you get 0.86. Now what about the probability of A union B? So that equals 1 minus the probability of A complement intersect B complement, which we were given this probability, so that's 1 minus 0.24, which gives us 0.76. And this concludes this video. I hope this was helpful.